Intermolecular forces describe how covalent molecules are attracted to each other. We know that in ionic compounds, the positive and negative ions experience electrostatic attraction on the positively charged cations and the negatively charged anions. Intermolecular forces, though, describe how covalent molecules experience attraction. In other words, in a covalent compound, how are the different atoms or groups of molecules held together? There are three types of intermolecular forces that you will need to know. The first one is called London dispersion forces. The second is called dipole-dipole attraction. And the third one is called hydrogen bonding. So for each of these three intermolecular forces, you will need to know three things. What is their relative strength? What actually creates the force and the attraction? And thirdly, how do you know which type of force is going to occur within a particular covalent compound? So let's start with London dispersion forces. Or LDF for short. First of all, you need to know that this is the weakest intermolecular force of the three that we've previously discussed. So the next question is, what actually creates this London dispersion force? Well, first of all, it's temporary. That's the reason why it is so weak. It results in when the electron cloud temporarily shifts to one side of an atom or one side of a molecule. And it creates a positive and negative end to the molecule. So what happens is the positive end of the molecule was attracted to the negative end of a different molecule. That's why these are called intermolecular forces. However, since this is temporary, the electron cloud will usually shift back to its normal pattern, and that will mean that there will be a loss of the attractive force. So that's why these are extremely weak. Where do we find London dispersion forces? This is how noble gas atoms are attracted to each other. And this is also how molecules that are normally non-polar experience attraction. Remember, nonpolar means that they do not normally have any dispersion of positive and negative charge. Right? It's usually equally dispersed, so there's no positive or negative end. However, since we have this temporary shift of the electron cloud, even in a nonpolar molecule, you'll get a temporary positive and negative end of the molecule. It's important also to understand that when this occurs, this tends to create what we call an induced shift of the electron cloud in the next molecule over. Okay, so because this one suddenly has a positive or negative end, okay, its positive end tends to pull the electron cloud from the molecule or atom that's next to it, making that one also have a temporary shift. So it creates a little bit of a chain reaction, but then the original molecule goes back, and the chain reaction goes back to its original nonpolar state. So this is a very temporary and weak force. The next type of force is called dipole-dipole attraction. This is the medium strength attraction. Okay, it's created when the positive end of a polar molecule is attracted to the negative end of a different polar molecule. This is similar to the London dispersion forces, where you have a positive end attracted to a negative end, but these are different because these are permanent. You have a permanent positive and negative end, not a temporary positive and negative end. So the positive negative end is called the dipole. So you have the two poles on one molecule are attracted to the two poles on a different molecule. Okay? Positive to negative, negative to positive. That's what we call dipole-dipole. So you will find this in any polar molecule. Will have dipole-dipole attraction. The last type of intermolecular force is called the hydrogen bond. This is the strongest. It's kind of a super strong dipole-dipole. Well, what creates it? If you have a hydrogen in your molecule bonded to either chlorine or oxygen or nitrogen. And the reason that these are important is because if the hydrogen is bonded to one of these, the electronegativity difference between hydrogen and chlorine, hydrogen and oxygen, or hydrogen and nitrogen creates a really polar molecule. So if you have a polar molecule, you look at it very carefully and you say, okay, it's a polar molecule. And remember, the rules for polar molecules are, if there is a lone pair on the central atom, it is a polar molecule. Or if the molecule is asymmetrical, which means it's a little lopsided on one side or another, has two different looking sides, it is also a polar molecule. So if you look at your Lewis dot structure and you know it's a polar molecule, you know you could have dipole-dipole, but you need to just double check to see if it's hydrogen bonding, the super dipole-dipole. So you look at your Lewis dot structure and you say, does there hydrogen occur in the formula, and what's the hydrogen bonded to? If the hydrogen is bonded to chlorine, oxygen, or nitrogen, it will be hydrogen bonding. So let me give you a quick example of what this looks like. I'm going to use water, because water is a very polar molecule. And it's a very polar molecule because it has oxygen bonded to hydrogen. Now, because of the lone pairs, this is the negative end of the molecule. This is the positive end of the molecule. So if there's another water molecule close by, it is the negative end and a positive end. So the attraction between this negative end of this water molecule and the positive end of another water molecule, this right here, that is what we mean by when we say hydrogen bond. Okay, it's always the hydrogen end, hydrogen is usually the positive end, is attracted to the negative end of another molecule. Okay, if the hydrogen if this was a nitrogen instead, this was like NH3, then the N would be the negative N, and the hydrogen on one NH3 would be attracted to the N on another NH3 molecule. So the trick is, when you're trying to look at a substance and determine what type of intermolecular force is present, first of all, if it is a noble gas, it'll be LDF, London dispersion forces. If it's not a noble gas, then you may have to sketch the Lewis dot structure very quickly and ask yourself, is this a polar or a nonpolar molecule? If it's nonpolar, it will also experience London dispersion forces. If it's a polar molecule, it could be dipole-dipole. But you need to look at your molecule again and say, is there a hydrogen bonded to Cl, O, or N? If it is, then it's not dipole-dipole. It's a really, really strong hydrogen bond.